spectroscopy, and I guess the hardest part has been over for you. Then if the theory is past you, well, there will be a bit of theory, I think, in every spectroscopy lecture, but I hope it's relatively easy to swallow. So let me remind you where we are today in the electromagnetic spectrum when we talk about vibrational spectroscopy. Yesterday you have heard from Serena on X-ray absorption spectroscopy that involves radiation with a few thousand electron volts. So when the photon hits the molecule, there is an earthquake going through the molecule. Electrons are being either excited from very deep core levels or into the continuum. And so that is a very brutal spectroscopy. Very subtle effects, but very brutal spectroscopy. Then we did talk about UV-Vis spectroscopy that uses radiation on the order of, say, 1 to 4 or 5 electron volts, which corresponds to the energy of chemical bonds. And so I talked to you about the spectroscopy is optical spectroscopy that is looking into the bond, and everything else that falls at lower energy is looking at the consequences of bonding. Now, when you go down to about 0.1 to 0.01 electron volts, the radiation is in the infrared region of the spectrum, and the molecular phenomenon that you study there is molecular vibrations. Now, if you go further down in photon energy, you go to the microwave region, and then the energy of the radiation is not even enough to induce a nuclear transition, let alone an electronic transition. Then you're in the domain of EPR spectroscopy, and you flip electron spins. And when you go further down to 10 to the minus 6 to 10 to the minus 7, you just flip nuclear spins, and then you're in the domain of ENDOR and NMR spectroscopy. So you will hear all about that from the colleagues in the lectures to come. And today we zoom into the infrared region of the spectrum, into IR and Raman spectroscopy. I will give you a brief introduction into the subject by taking a bird's eye view of what you can do with these spectroscopic methods, and then talk to some extent about molecular vibrations, how they're being constructed, what is the nature of molecular vibrations. So we will talk about vibrational frequency and normal coordinates, and then we will talk about the physical origin of IR intensities, Raman intensities, and then resonance Raman intensities. We will briefly move into experimental techniques and then talk about some applications in bioinorganic chemistry. So why would you want to do vibrational spectroscopy? So there are very many reasons to do that. So every spectroscopic method has its particular strengths and also its particular limitations. That's why it's always a good idea to use more than one spectroscopy and apply it to your system. It's like touching the elephant from every side, rather than only touching like one specific part of it and drawing great grand conclusions. There usually is one best spectroscopy, but it's, at least in my experience, it's much better to analyze the information content of like 4 different spectroscopies to 80% than 1 to 99%. So in terms of vibrational spectroscopy, you obtain structural information. You can, and that is probably the largest use of it, is to identify fingerprint characteristic vibrations of functional groups in molecules. You can use isotope shifts, as we will talk about in a minute, to identify certain functional groups. You can couple that to normal coordinate analysis, and altogether that gives you quite a bit of insight into geometric structure. It also contains electronic structure information, and here particular resonance Raman spectroscopy contains a lot of electronic structure information, and we will work this out with a few examples throughout the talk. It can help you to identify and design electronic transitions, and it will give you a lot of insight into chemical bonding. Now you can use it when you study reaction mechanisms. And if you combine it with techniques like freeze quenching, which you will hear about in that course later, or continuous flow techniques, you can use it to characterize intermediates. It can be combined with electrochemistry, stop flow, and other techniques. So it's very versatile techniques in order to characterize and detect reaction intermediates. And it's nicely complementary to other techniques in that it is not dependent on the molecule having to be magnetic as in EPR or MCD spectroscopy. It has much higher resolution than absorption and CD spectroscopy. In fact, you can use the resonance Raman spectrum to reconstruct vibronically resolved absorption spectra, which you almost never get for any polyatomic molecule. And last but not least, it is not limited to certain isotopes like Mörs-Bauer spectroscopy is. So taken together, it's a very, like vibrational spectroscopy occupies an important niche in the bioinorganic spectroscopist's toolbox. Now, the experiments for IR spectroscopy and Raman spectroscopy are fairly different. IR spectroscopy, on the simplest level, you can think about it just like an absorption experiment, so just like your absorption spectrometer, just with infrared radiation. So you have an IR light source, you have a sample cuvette, a reference cuvette, you have an IR detector, and then the signal goes to the computer, and using the Lambert-Baer law, the infrared absorption is minus the logarithm of the intensity of the detected radiation divided by the reference intensity, and that is equals the extinction coefficient times the width of the cuvette times the concentration of the species. So far, so good. The Raman experiment is totally different, and although you detect phenomena that correspond to infrared quanta, the light that you use is invisible, and that is an advantage because all the tools for engineering visible light are very highly developed and very powerful. And so you have a laser that is operating either in the visible or sometimes very often a neodymium YAG laser is used that operates a little over 1,000 nanometers. That hits a sample, and rather than studying absorption, you study scattering. And you can use a variety of geometries to detect that scattering. It can be 90 degrees, or it can be total backscattering. It can be 135 degrees. Now, the majority of that scattered radiation ends up having the same frequency as the incident light. And that is so-called Rayleigh scattering. And so first of all, you get a hugely intense line, which is called the Rayleigh line. This is absolutely boring. It contains no information that you could be interested in. But then if you zoom in by several orders of magnitude, you will find these side bands. And so if you look at energy of the scattered radiation that is a little lower than the incident radiation, you will find a few lines that are called Stokes lines. And if you look at higher energy, then you will find anti-Stokes lines. So the more useful ones of these are the Stokes lines, and the anti-Stokes lines refer to hot bands. But you might have incentive to study those, but normally you would go here to this side and study the Stokes lines. And the Stokes lines, they correspond to inelastic scattering, so where the frequency of the scattered light is different than the frequency of the incident light. And you will find that these peaks occur relative to the Rayleigh line at the energies of molecular vibration. So in principle, you see peaks at the same position as in the IR spectrum. That is emphasized here for this small molecule methyl dithioacetate, where you have the infrared spectrum here and the Raman spectrum on the bottom. And you see that they basically have peaks at the same positions, but they have different intensities. And that the reason for that is that the selection rules for Raman spectroscopy and infrared spectroscopy are different. So they have different intensity mechanisms. In fact, if your molecule has inversion symmetry, center of inversion, IR and Raman are strictly complementary, then you will have an IR band only if the vibration is antisymmetric relative to the center of inversion, whereas in Raman you will only see it if the vibration is symmetric. Now, this molecule doesn't have a center of inversion, and so you have bands that are simultaneously IR and Raman active, and so you see they nicely line up. The intensity of the scattered radiation is strongly dependent on the frequency of the incident light, and it goes up as the fourth power of the frequency of the incident light. So hence it is in principle an advantage to go into the blue region of the spectrum. Yeah, however, commercial instruments usually work at higher frequencies, because in Raman you don't want, if you do a standard Raman experiment, you don't want your molecule to absorb the radiation. Yeah, so you just want the scattering. Resonance Raman occurs if you have incident light that falls within the region of an absorption band, and that is the strength of that technique. Now, if you think about metalloproteins, obviously you have molecules with thousands of atoms. Now, obviously, if you have thousands of atoms, you know you have thousands of vibrations. In principle, that also means you have thousands of peaks in your vibrational spectra, and this is something that can barely be sorted out. It is pretty much impossible to understand that in detail. So you would, at first glance, think that IR and Raman spectroscopy are really not that useful when you apply it to biochemical problems. However, people have found, and largely empirical so, that both IR and Raman spectroscopy are globally sensitive to secondary structure elements like beta sheets or alpha helices. So if you're interested in that type of thing, and so for example, to detect a protein conformational change, IR and Raman spectroscopy are useful. However, if you are interested in a little more detail, then the by far most useful technique for biochemistry is resonance Raman spectroscopy. And why is that so? If you have a chromophoric group in your molecule, for example, such as a heme here, it has a nice absorption spectrum. Now, if you tune your laser for the Raman experiment into such an absorption band, then vibrations that are coupled to the chromophore, so that are local to the chromophore, get enhanced in their intensity by several orders of magnitude. So among the mass of thousands of vibrations, you're able to filter out the ones that are associated with the chromophores. Since those chromophores are usually the active sites of those enzymes, it means you have a selective way to probe the active site of that enzyme. So that is a fantastic technique that has found widespread use in bioinorganic chemistry, and it is something that can be used to great advantage. In IR spectroscopy, what has been found useful is very highly sensitive difference Fourier transform IR spectroscopy that provides you with information about changes in parts of the protein. These data that come from FTIR might be quite challenging to interpret. There are also lucky situations in which you will have vibrations that interest you in non-crowded regions of the spectrum, so where like the protein doesn't absorb much. These situations happen, for example, when you detect CO, CN, or NO vibrations that you may be able to detect in IR spectroscopy, even like for the whole protein. Very famous example is hydrogenase, where IR spectroscopy has provided a lot of information. Yet, of all of these possibilities, resonance Raman spectroscopy is certainly the most versatile technique among the vibrational tools. So with that overview, we now slowly build up the physical content of these spectra by taking a look at vibrational frequencies and normal modes. So yesterday, I told you a long story about solving the Schrödinger equation for molecules, the Born-Oppenheimer-Schrödinger equation, and I told you that for any given fixed geometry, if you solve the Born-Oppenheimer, the electronic Born-Oppenheimer-Schrödinger equation, what you get is a total energy. Now, if you repeat that point by point, you get what you call a potential energy surface. That is a very unfortunate word because, of course, the energy that you calculate as a solution of the electronic Born-Oppenheimer equation does contain the kinetic energy of the electron. So calling it a potential energy surface to some extent is misleading. Now, I've talked a lot to you about what you can do with these total energies, how you can use it to predict reaction rates and dissociation constants and redox potentials and all kinds of things like that. But today we take a different point of view. So these potential energy surfaces are the playground on which the molecular vibrational problem takes place. Now, so we let us assume we can solve that Born-Oppenheimer-Schrödinger equation, and we get the total energy, and we map it out point by point from here to here to here to here to here. So we map the potential energy surface along a bond. So that could, for example, be the stretching coordinate for a diatomic molecule AB, where you have equilibrium geometry here, and then you stretch and stretch and stretch and stretch and stretch, and eventually you dissociate the molecule into isolated atoms A and B. So the difference between the bottom of the well and the dissociation limit, that is called the dissociation energy, dE. Yeah, and so where that occurs, like how deep that well is, that obviously depends on the strength of the bond. Yeah? And so we will concern ourselves with the shape of that potential energy surface, in particular near that equilibrium distance. And in fact, if you look at it carefully, it looks pretty much like a parabola close to the minimum, and that is called the harmonic region. Yeah? And the harmonic region of the potential energy surface, that is the most decisive region that we need to study in order to understand molecular vibrations. Yeah? So let us come to a simple classical model that contains all of the essential physics here. So we're assuming that we can approximate the potential energy surface close to the equilibrium as a parabola. And then our model of the molecule is simply the following, that we have two atoms, and the only thing that matters here is the masses of these atoms, Ma and Mb, and they're held together by a spring with a force constant K. Yeah? So, and that K, as you will see, is related to the shape of the potential energy surface. So if we use that simple model and put it into Newton's law, yeah, so that is entirely classical physics, we will find that the force, of course, is the gradient with respect to the bond distance, and by Newton's law that equals the reduced mass times the second derivative of that bond distance with respect to time. So the solution of that differential equation is then the trajectory r of t that I talked about yesterday. That is the trajectory. It's the internuclear distance as a function of time. Now we need to specify that potential V of r, and we can make a Taylor expansion of that potential around the equilibrium distance, yeah? And so we have a V0 term that is like the value of the potential at equilibrium distance. Then we have the first derivative of the potential with respect to the internuclear distance times the difference between the value of r we are asking for and the equilibrium distance r bar. Now, of course, that gradient at the minimum of the potential energy surface well is vanishing, so that is 0. That means the first term that survives in the Taylor expansion is the second derivative of the potential with respect to nuclear distance taken at equilibrium distance. Yeah, and then multiplied times the displacement of the nuclei from their equilibrium geometry squared. So it is then that second derivative of the potential energy surface at equilibrium distance that we identify with the force constant K. Yeah? And that means inserting this here into Newton's law, we get this very simple looking differential equation for the internuclear distance as a function of time. Now you can go to your math lectures or your formula collection in order to figure out what the solution of that equation is, and you will find that the internuclear distance as a function of time starts out as the equilibrium distance, and then there is a sine and a cosine term that will lead you to oscillatory behavior. That is simply like then the oscillation of the diatomic molecule, as a function of time, and these constants C1 and C2 depend on where you start the vibration. So you need to start in some stretch geometry and then release it, and then it will make a harmonic motion around the equilibrium distance. And the frequency with which that molecule will oscillate is called the vibrational frequency, and it's 1 over 2 pi times the square root of the force constant divided by the reduced mass. And the reduced mass, m, equals the product of the masses of the two atoms divided by their sum. So that is the definition of the reduced mass. Yeah, so let's recap that. The molecule, the classical motion of a diatomic molecule defined by two masses A and B held together by a spring with a force constant K is 1 over 2 pi times the square root of K divided by m. Yeah? So that means the frequency of the harmonic motion will be the higher, the larger that force constant K is. Yeah? So and that means like the more stiff the parabola is. Now, that is clear. Now that the frequency is proportional to the square root of the force constant, no problem. And an interesting feature here is the reduced mass. And we can use that to our advantage in chemistry via the so-called isotope shift. Now, if you take that equation here for the vibrational frequency and look at the equation for the reduced mass, as I said, ma times mb divided by ma plus mb. And now, as a synthetic chemist, you can make a change in these masses by using different isotopes. For example, if these atoms are oxygens, you could replace the naturally abundant 16O with 18O. That might or might not be an expensive experiment for you to do, but you can do it. And so if you ask yourself, what is then the change in the vibrational frequency relative to the non-labeled diatomic, you will find that nu prime, that is like the changed vibrational frequency, is given by this relatively simple equation. Now, if you put the values in for a replacement of 16O by 18O, you will find that the vibrational frequency for an 18O dioxygen is lower than that of 16O by 5.7%. Yeah? And so if you do that labeling and you have a change in the vibrational frequency of a given mode by 5.7%, you have positively proven that it is associated with motions of the oxygen in the system. And so in a complicated vibrational spectrum, this is a fantastic way of like putting your finger into the wound and like making sure you understand what the origin of the vibrational band is. So isotope labeling is a key component of vibrational analysis in vibrational spectroscopy. Now let's look a little bit at the information content of the force constant. First of all, let's briefly talk about something that everybody hates except physicists. So these are only people who can do it, and that is units. So, yes, seriously, I'm not kidding. I'm not a physicist. I hate it too. Yeah, so the force constant is the second derivative of the potential energy with respect to internuclear distance or coordinates. So that means it has the dimension of energy per area. And so if you put numbers in, so a good unit would be 10 to the minus 18 joules per angstrom squared. But that is not what people use. For some historical reasons, the unit used in vibrational spectroscopy is 10 to the 2 Newton per meter, which happens to be the very odd unit of millidyne per angstrom. Yeah, so now you know why nobody likes that. But this is the commonly used unit in vibrational spectroscopy to express force constants. And now let's, just to get you oriented, what is a large and what is a small force constant? Let's look at some typical force constants. Now, N2 is one of the strongest, stiffest bonds in chemistry, has a force constant of 22.4 millidyne per angstrom. A typical single bond like H2 or F2 have values around 5 millidyne per angstrom. Double bond of O2 has 11.4 millidyne per angstrom. CO and NO, strong bonds, have 15 to 80 millidyne per angstroms. Yeah, so you see that these force constants become large if the bonds are strong. But that's not quite the right way of putting it. These force constants become large if the bond becomes stiff. Yeah, so it's resistant against stretching it. Yeah, so that is really what the force constant tell you. However, many people, I think, and it's quite intuitively appealing that you think if the bond is hard to stretch, then it's also hard to break. And that means there should be a relationship between the dissociation energy and the force constant. Yeah? And that is generally so. And the second trend is that, of course, the bonds that are stiff also tend to be short. And that particular relationship between the length of a bond and the force constant, that has been made quantitative a long time ago by a person called Badger. And so there is a thing called Badger's rule, and it states that the force constant, the diatomic stretching force constant, Kij, is roughly equal to 1.86 times the inverse third power of the equilibrium distance minus an empirical constant Dij. And so for a number of atom pairs, Badger gives values for that constant Dij. So if I is a hydrogen and J is a hydrogen, then the value of the constant Dij is 0.025 if the equilibrium distance is expressed in angstrom. Yeah, and so if you have a first row atom and another first row atom, the value of Dij is 0.68. So that means you can, in principle, take vibrational frequency information and get a fair estimate of bond distance, if you so desire. It's a very empirical relationship, but it generally holds to be true to reasonable accuracy, so it is a useful tool for vibrational spectroscopy. Now, if you look at how good is the relationship of force constant to bond strength, to dissociation energy, you see that there generally is a trend of, if you have a higher force constant, you also get a higher dissociation energy, but there is quite some scatter. The simplest model to understand that relationship is to assume a non-harmonic potential, which is a Morse function. So that Morse potential curve here is the simplest model of a dissociative, like of a potential energy surface, all along to dissociation. And generally speaking, it is not a bad model. So if you really calculate the dissociation curve of a molecule, and you can often fit the points that you get to a Morse potential to a reasonably good approximation. But beware, if you do so, most quantum chemical methods will fail when you really dissociate a bond. That's a totally different story. But if you go to your computer and say, oh, that's cool, that's what I do. I put in my diatomic and I stretch it, boom, and then I get a good potential. You will find that in many cases you get some pretty funny looking curves that are quite unphysical. That has a lot to do with the way we do our quantum chemistry today, and it will eventually require some awareness of the shortcomings of these theoretical methods. But let's assume for a moment that we can solve our Born-Oppenheimer-Schrödinger equation exactly. Then these dissociation curves roughly will look like Morse potentials. Now, so the equation for the Morse potential is the dissociation energy times the square of 1 minus the exponential of a decay constant beta that is measuring the stiffness times r is the internuclear distance. Now, if you calculate the force constants by taking the second derivative of this as equilibrium distance, you will find that the force constant in the Morse potential is 2 times the dissociation energy times that decay constant beta squared. So that means that within the Morse potential model, the force constant is indeed directly proportional to the dissociation energy. Now, this is actual experimental data that tells you that there are deviations from that, meaning that the Morse potential is not a perfect representation of the potential energy surfaces of these molecules. For example, here KCl or NiCl or CO, they're not perfectly following the Morse potential, but it's close enough to justify the observed trend. Yeah? So, generally speaking, if you have a large force constant, you will have a short bond. If you have a large force constant, you will have a strong bond, meaning a large dissociation energy. Good. But the molecules that we're having are not classical, and they're not moving classical like masses on a spring. They're moving according to quantum mechanics. And so that brings us to the quantum mechanical harmonic oscillator. So we're going back now to the situation where we can approximate the potential as an harmonic function, so as a parabola. And now you need to solve the vibrational quantum mechanical expression. So I told you yesterday that if you separate the full molecular Hamiltonian via the Born-Oppenheimer equation, you get an electronic energy equation, which we talked about yesterday, and you get a nuclear equation. And now that nuclear equation is the one that you have to solve for the quantum mechanical equivalent of the nuclear motion, and that is the nuclear wave function. And now for a harmonic oscillator, you will find that it has a fairly peculiar behavior, because all of the energy levels are equally spaced here for a harmonic oscillator. So, and these are the vibrational energies for like a single quantum mechanical harmonic oscillator, and they're given by n plus 1/2, where n is then the vibrational quantum number, times h nu, which is the frequency, which is the energy of the oscillator. That means that there is vibrational energy even in the lowest vibrational state, n equals 0. So n equals 0, and that still has like half a quantum of vibrational energy. This is an oddity of quantum mechanics, but it is also found to be true. So that is a 0-point vibrational energy. It is also something that you need to take into account if you, say, calculate equilibrium constants or other thermodynamic quantities. It is something that comes on top of your electronic energy you get from your quantum chemistry. Yeah? So in terms of putting it into perspective, the full molecular many-particle combined wave function is taken as a product of an electronic wave function and a vibrational wave function. The total molecular energy is then the energy of the ith electronic state plus the energy of the vibrational state you're in. Yeah? And the vibrational wave functions, they look like I've displayed here in blue. They're so-called Hermite polynomials multiplied by a Gaussian shape and a Gaussian function and a normalization factor. In the lowest vibrational state, that is simply a Gaussian function here, and so as if you get like your quantum mechanics straight, then the square of the vibrational wave function is the probability distribution of meeting the nuclei at a given position. So what that tells you here, that is already the square of the nuclear wave function. What that tells you here, that in the vibrational ground state, you have the highest probability of finding the nuclei at equilibrium position. That's not a big surprise, isn't it? Now, in the vibrationally excited states, you see that the maxima of the probability distribution move closer and closer to the rims of like the potential energy surface, the harmonic potential energy surface, and there are these oscillatory behaviors. So with each additional vibrational quantum number, there is an additional node in that probability distribution. Yeah? So I hope you can picture that this is a probability distribution of meeting the nuclei at a given internuclear distance. So that is the meaning of the vibrational wave function, and that is the nature of the vibrational energy levels of an harmonic oscillator. So each and every vibrational mode of a given system will have this behavior in the harmonic approximation. Obviously, the harmonic approximation is an approximation, as we have seen, that the potential is not quite a parabola, but is anharmonic. Yeah? So there are deviations from the quadratic behavior. But since almost every potential is well approximated by the harmonic behavior, it is not that we take a fresh start for each potential energy surface, but we express deviations from the harmonic behavior. So that is why you write in the real world, so for a real oscillator, not a harmonic oscillator, you write the vibrational energy as the vibrational quanta times n plus 1/2, that is the harmonic part, minus xe, that is an n-harmonicity constant, and it goes by n plus 1/2 squared. And so already the leading correction to the harmonic behavior is typically getting you very close. What will happen in a real oscillator is also that the energy levels are no longer equally spaced, but they're closer than equally spaced. That's why you have a minus here. Yeah? So the spacing between these levels gets closer and closer and closer as you go up here, and eventually they will approach a continuum as you will approach dissociation. Yeah? So that is where you reach the scattering limits. The zero-point vibrational energy will also tell you that what you measure is not quite the dissociation energy dE, but is a quantity d0 that differs by vibrational quantum from dE. Yeah, so that is the observable quantity. Now here is something important that you need to understand. Now if you go to your quantum chemistry program and you ask the quantum chemical program then is, please predict the vibrational frequency for me, what it will predict for you is the harmonic frequency. Yeah? The harmonic frequency will always be a bit larger than the true frequency. So when you then go to your computer program and the computer program spits out and says 720 wave numbers for your vibrational frequency, and then you go to your spectrum and say, ha, look at this, I have a peak at 1720 wave numbers. So my calculation is fantastic. The reality is your calculation is not fantastic. Yeah? It has overestimated the frequency because in reality all frequencies are anharmonic. Now, these deviations are usually systematic. That's why what people do is simply scale those calculated frequencies by a constant factor. And so what goes in there are intrinsic errors in the method, intrinsic errors in things like the basis set, and of course like a global correction for n-harmonicity. If you really want to calculate n-harmonic force constant, life becomes pretty miserable with quantum chemistry. This is like a lot of effort, it's very expensive, and normally you don't do that. So normally you calculate harmonic frequencies, but then when you compare them to experiment, you've got to be aware that what you measure are the true frequencies which are anharmonic. Yeah? So that, that is something that is not quite unimportant to keep in mind. Yeah? So now let's talk about vibrations of polyatomic molecules. Now, in a polyatomic molecule, many vibrations are possible, obviously. As we have seen for a diatomic molecule, you only have one possible vibration, which is a stretching vibration with one eigenfrequency, and that means one vibrational mode. Now, as I'm sure you have heard before in your chemistry curriculum, like for an n-atomic molecule, you have 3n minus 6 possible vibration, or if the molecule is linear, you have 3n minus 5 possible vibrations. Yeah? That means you have 3n minus 6. So I will not make that special distinction now all the time just to save talking time. Yeah? So if you have a polyatomic molecule, you have 3n minus 6 vibrations. That means you have 3n minus 6 vibrational frequencies. And you have 3n minus 6 so-called normal modes. So that stretching motion that we've seen for the diatomic molecule is only one particular type of so-called normal mode. Yeah? So what a normal mode really is the shape of molecular vibration. And in general, all atoms move in each normal mode of a molecule. That means that these vibrational modes, these vibrational motions are fairly delocalized in a polyatomic molecule. As much as we love to think they are strictly localized, so that we really say a CO stretching frequency, the reality is that they spread out over the molecule in quite a bit. And I think it is very important that one is aware of that, because there are some fairly wrong conclusions that are have been taken from experimental data by assuming these vibrations to be much more local than they in reality are. Yeah? Okay, so the general types of vibrational motions that you will have in a polyatomic molecules are stretches, as we had them for diatomics. Then bendings, so where you basically change the angle between three atoms, and torsional motions where dihedral angles change. These are the three basic types of motions that you have. Now, typically, a normal mode will contain contributions from stretches, bends, and torsions. So what are the -6? So what are the motions that don't count, that do not go into the vibrational modes of a molecule? These are rotations and translations. So that's why it is not 3n vibrations, but it's 3n-6 vibrations, because if you translate the molecule as a whole along the x-axis, the y-axis, or the z-axis, that there is no restoring force. Yeah? So you don't stretch any bond, you don't change any angle, you just translate the molecule as a whole. There's no restoring force, and hence the vibrational frequency is 0. And equally, if you rotate the molecule as a whole, there also is no restoring force, and hence there is vibrational frequency of 0. The only exception is for a linear molecule, the rotation around the bond does not count as a rotation, and that's why it's 3n-5 for a linear molecule, is the degrees of freedom. Now, a pretty good test, if you calculate vibrational frequencies, and your computer program does not project out these translations and rotations offhand, you should have these 6 vibrational frequencies that are 0. If these 6 vibrational frequencies are not 0, then your calculation is in trouble. Now, if these deviations from 0 are, say, 0.1 wave numbers or 0.01 wave numbers, there is nothing to worry about. If these deviations are 100 wave numbers or 50 wave numbers, your calculation is seriously wrong, and you cannot use any of the results that the computer program has told you. So that's why it is important to be aware that there should be these 6 zero modes in a full vibrational analysis. Let's look at an example. And I think that is a classical example that everybody is showing, is the normal coordinates of water. So water is a triatomic molecule, so it has 3n-6, has 3 degrees of vibrational freedom, and they fall into 3 vibrational modes. And obviously these vibrational modes, they have symmetry. Yeah, and so you display them with these arrows here. So the first vibrational mode is a bending mode, where basically the 2 hydrogens here at the corners are moving out while the oxygen is slightly moving in. That is a totally symmetric vibration that has symmetry A1 in the C2V point group that the water molecules belongs to. And experimentally, it's found at 1595 wave numbers. The second vibrational mode is the symmetric stretching vibrations, where the OH bonds stretch in phase, so they do this motion here, and it's found at 3652 wave numbers, and that is also a totally symmetric vibration. And the third one is an asymmetric vibrations, where the 2 OH bonds stretch out of phase. That is found at 3756 wave numbers. So normally, if you would naively assume that these vibrational modes are really very localized, you would assume that there should be 2 vibrational frequencies that belong to OH stretching that are at the same value. But that's not true. They talk to each other, and that difference here, 3,756 minus 3,652, that is the interaction between these two OH stretches that therefore split into a symmetric stretch and an anti-symmetric and an asymmetric or anti-symmetric stretching vibration. Yeah? And as you can see here, you can observe these vibrations both in the IR and the Raman spectrum. Yeah? So these are the vibrational modes of water. Vibrational coordinates of CO2. So there are 4 of those because it's a linear molecule. Here you have at highest energy an antisymmetric stretching vibration where the two CO bonds stretch out of phase. Then you have symmetric stretching vibrations where they stretch in phase at 37 wave numbers. So you see here the splitting between the antisymmetric and symmetric is huge. Yeah? Then there is an out-of-plane bending mode where the two terminal oxygens move opposite to the central carbon, and there is an in-plane bending mode. And so this is a degenerate set of vibrations, so that they only differ in the direction of their movement. They are found at 667 wave numbers. So just as there is degeneracy in electronic states or orbital energies, there also can be degeneracy in vibrational motions. Now, so what we've seen now is that vibrational modes are characteristic, and they're characteristic not only for pairs of atoms, but they're characteristic of functional groups. And chemists have made very good use of that for a very long time, and that's why in many organic chemistry textbooks you will find tables like the following, where you have so-called group frequencies, where people have written down where certain functional groups typically resonate in an IR spectrum. So in alkanes, you will find CH stretching vibrations in the region 2,965 to 2,850 wave numbers. In alkanes, it's a bit higher than that. You have CC stretching vibrations that are different. In alkanes, it's about 700 to 1,200 wave numbers. Double bonds resonate at 1680 to 1620 wave numbers, triple bonds in 2260 to 2100, and so on and so forth. So these are your empirical correlations in these vibrational group frequencies that if you apply vibrational frequencies, you should have a thing like that hanging on your wall, or you have to have it memorized, because that is really like the playground that gets you oriented where you roughly expect what in a vibrational spectrum. Now, in the general case, when you want to get insight into these vibrational frequencies in detail, the process of doing that is called normal coordinate analysis. And so normal coordinate analysis in the general case works like that. So if you have a polyatomic molecule, the quantity that you want to calculate is the second derivative of the energy with respect to nuclear coordinate, as we have seen for the diatomic case. But the generalization for that to a general n atomic molecules with 3n nuclear coordinates is the so-called force constant or Hessian matrix. And so the Hessian matrix F is the second derivative of the electronic energy with respect to two different nuclear coordinates, say XA and YB, where A and B are atoms, and X and Y might be like the X coordinate and the Y coordinate of a given nucleus. Now you have to weight the Hessian matrix with the atomic masses, and you turn it into millidyne per angstrom by multiplying with 15.57 and dividing by the square root of the product of the masses of the two atoms. Now if you diagonalize that matrix, you will get the eigenvalues of the mass-weighted Hessian matrix and the eigenvectors. And from the eigenvalues of the mass-weighted Hessian, you get the vibrational frequencies in wave numbers now as 1,302.78. This is a unit thing. Then if you want to dig deeper, then go to a physicist and let him explain to you how you go from millidyne per angstroms into wave numbers. And so it is 1302.78 times the square root of that eigenvalue of the mass-weighted Hessian. That gives you the vibrational frequency of the ith vibration. And the normal mode follows by inverse mass weighting from the eigenvectors of the mass-weighted Hessian. So that is how you would do it in a computer. So you would do it forward, so to say, ab initio. That is how you predict the vibrational frequencies, harmonic vibrational frequencies, and normal modes for a general molecule. So that is fantastic if you have an accurate force field and a good quantum mechanical method. And so the deviations that you have reflect the shortcomings of the theoretical methodology, and they reflect the shortcomings of the harmonic approximation. This is not how it's historically done. Historically, people didn't have computer programs to predict vibrational frequencies for them. They did it all by hand. And so what they're doing is to basically construct such a Hessian matrix by hand using a so-called force field of the molecule under investigation. Now, today, I would say 99.9% of vibrational analysis is done this way. And if you run into a real old school guy, they will do the not me. They will do the force field by hand. And for example, if you have a group like this, say you have a manganese with a double bond oxygen and an OH group, you will have to dig out, or you will have to define the force field by defining motions of these nuclei that you associate with force constant. So you will have an MNO double bond O stretching force constant. You will have the MNOH stretching force constant, the OH stretching force constant. You will have an OMNO bending, and so on and so forth. So these are just 4 atoms, and you already have quite a number of coordinates. So say you have a good feeling for it, you can choose relevant internal coordinates, SI, and then you guess the force constant matrix, so you associate values with all those force constants, then you include the masses and geometrical parameters, and historically this is known as the FG matrix approach to vibrational spectroscopy, and there's a classic text by Bright Wilson who will explain to you how you do that. You get it for a few bucks from Amazon. It's a very nice text. And so when you do that, you get frequencies and normal modes. And very typically what has been done is then to fit these force constants that you have here to experimental data. That is a fairly involved procedure. You will appreciate that you can only do that for molecules with very few atoms before you run out of steam, because these force fields get huge. They also get over-determined, then it's because there are always more of these internal coordinates that there are degrees of freedom. So these force fields are not even unique. So you can generate them, but like the next person who has a different chemical intuition than you have will create a different set of force fields, and so he will come up with different values of these force constants. So these force constants, as intuitive as they are, they're not physical observables. The physical observables are the vibrational frequencies. Yeah. The advantage that you have from models like that is that you may get insight into classes of compounds. So we'll now move into vibrational intensities. Now, as you've seen, we have these 3n-6 harmonic oscillators, even if we stay within the vibronic, in the harmonic approximation. And now they all have these large, if not infinite, number of vibrational states. Now, the most important vibrational transitions are those that lead you from the vibrational ground state to the first vibrational excited state. These are called the fundamentals, and the energy of fundamental is obviously 1 vibrational quantum delta E equals h times nu. You can have hot bands that lead you from an excited vibrational level to the next excited level. That would be like n plus 1 to n prime n plus minus 1. That also come at 1 vibrational quantum. An overtone is the excitation of 2 or 3 or more vibrational quanta simultaneously, and hence the energy of those peaks are at 2h nu, 3h nu, and so on and so forth. And you can also have combination bands, where a combination band is you excite vibrational quanta of different normal modes, of different vibrational modes simultaneously. For example, one with a higher frequency and one with a lower frequency. That would be a combination band. Yeah, so you have to try to think in 3n-6 vibrational dimensions, which is quite a challenge, but if you like think it through and let it sink in, it will eventually make sense. Yeah, so the way we draw these figures, we can only draw them 2-dimensional because we can't draw something 3n-6 dimensional. But try to think in 3n-6 dimensions, and it'll work. It'll make sense. Yeah. I know it's hard. That is, yeah. Okay, to put that into perspective, I want to compare now the physics of IR, Raman, and resonance Raman spectroscopy. Now, so let's say this is the potential energy surface of our electronic ground state, and here are the vibrational levels of that electronic ground state. Then an IR fundamental transition will lead you from the ground vibrational level to the first vibrational level of the electronic ground state. So that is an IR transition. Now, a Raman transition is a bit more confusing. You have a much higher energy photon, and so if you're tuned out of an electronically excited state, what happens is that in Raman spectroscopy, it's kind of a virtual 2-photon process where you reach a virtual level that is not a real excited state of the system, from which you drop down by emission into a vibrationally excited state of the electronic ground state. Yeah? So that is the Raman process. You go from the vibrational ground level up to a virtual level and down into a vibrationally excited level, and that gives you a Stokes line in the Raman spectrum, and that is obviously the difference here. That is obviously also 1h nu, which is a vibrational quantum. Now, the resonance Raman experiment in principle is the same as the Raman, except for you really reach an actual electronically excited state of the system through the absorption of a photon, yeah, followed by the re-emission, so the scattering process into a vibrationally excited level of the ground state. So that is the resonance Raman process. Yeah? So that means Raman and resonance Raman only differ experimentally by whether you don't reach an actual excited state or you reach an actual excited state with the incident photon. Yeah? Now, you can observe very nice overtoning combination bands in resonance Raman spectroscopy. That is it's probably not the rule, but it can happen. So, for example, for this nice nickel coordination compound, you have a beautiful resonance Raman spectrum for which you observe like a long progression in one quantum as well as a combination band of 2 quanta. That is data of Spiro and Chernushevich. It is not the rule, but it is possible, and here it shows you how such a progression looks like. It's actually big fun to analyze data like that. Now, let's get into when do you observe an IR, when is a transition IR active, when is a transition Raman active, when is a transition resonance Raman active. Now, a transition is IR active, so if the molecule has a dipole moment, and that dipole moment is changing in the course of the molecular vibration. So basically what happens then is that you have an oscillating dipole. Yeah? So you have your molecular vibration. So you have a heterodiatomic, it has a dipole, it is vibrating, it's vibrating, and so the dipole is flickering. So that's an antenna. Yeah? And so the antenna will pick up the IR photon. Now, if you put that into into mathematical formulation, you will find that the square root of the IR intensity is proportional to the change of dipole moment with respect to the normal mode. Yeah? So you can take the first derivative of the dipole moment with respect to a given normal mode, and if that derivative is unequal 0, you will have an IR active vibration. Yeah? Now the Raman is more complicated than that because it does not depend on the dipole but on the polarizability. Actually, the change of polarizability with respect to a nuclear motion. So polarizability is the ability of a molecule to acquire a dipole moment in the presence of an external field. So you can think of like the first photon that you put in as creating an electric field that is like inducing a dipole in the molecule that is then picked up by a second photon. That's not quite the correct way of thinking about it, but it's a useful picture. So when you analyze it in mathematical terms, it is the change of polarizability instead of the change of dipole moment that gives you the Raman scattering intensity. Now it gets quite a bit more interesting in the resonance Raman experiment. That's why I will not dwell on the Raman intensity mechanism, because the resonance Raman intensity mechanism is more interesting. Now the polarizability tensor, alpha it is called, with K and L being Cartesian components, in principle contains a sum over all excited states of the molecule. So this is the correct expression for the polarizability tensor, and then the Raman intensity is proportional to the square of the first derivative of that with respect to nuclear motion. Now if you're studying the resonance Raman experiment, this polarizability tensor is not good enough because you need something that is called the frequency-dependent polarizability, because the induced polarizability will depend on the frequency of the radiation that you put in. And here's something that is called the Kramers-Heisenberg equation, which is a very famous equation in quantum mechanics, and also has a funny history that it's good to read about. There are history books on like the history of that equation. Now that looks very much like this expression, the frequency-independent polarizability, except it has two terms. Now look what's here in the denominator. So we have an infinite sum over excited states. Here we have an excitation energy from the ground state to the nth excited state, and here we have the energy of the incident photon. Now these two terms differ by having a plus sign here and a minus sign here. So what will happen if the energy of the incident photon is hitting an excitation energy? Then you get 0 here in the denominator, except for like a phenomenological damping parameter, I times gamma. And so the first term will blow up. Yeah? And so this is like the mathematical origin of the resonance Raman effect. That instead of like having contributions from all excited states, as you have is h nu is far from any excitation energy, you have a single electronic state dominating the polarizability. Yeah? And then the one resonant term here is the one you have to look at. So if we take the derivative of this, we get to the resonance Raman intensity mechanism, and it contains two terms. There is a smaller term here that depends on the derivative of the transition dipole moment with respect to normal coordinate. That will be non-zero for non-totally symmetric modes, but the more important one is this one, that is the frequency-dependent polarizability times the first derivative of the excitation energy with respect to the nuclear coordinate. So now that is important, because as the Hamiltonian of the system is totally symmetric, this first derivative will only be non-zero if the vibration is totally symmetric. Hence the conclusion. So if all of this is gibberish for you, like now listen to this sentence. The resonance Raman will be non-zero only for totally symmetric modes. Yeah? So it's as simple as that, and the mathematical justification for that is here. So what you will observe in a resonance Raman spectrum dominantly are totally symmetric vibrations. So it's very good for observing that type of totally symmetric stretching vibrations. Now in order to calculate that, it's quite hard, because what you would have to do is to calculate very high-dimensional Frank-Condon factors, and we and others have developed methods to deal with this via a very interesting yet quite unusual time-dependent formalism that roughly runs like that. So you think of the system as starting from the vibrational ground state, and at time 0 you propagate that Gaussian wave packet here to the excited state potential energy surface, and there it will undergo dynamics, because it is no longer a vibrational eigenstate on the excited electronic surface, and hence it will undergo a dynamic that you can describe as a quasi-time-dependent process with some fairly obscure mathematics that I'm not going into. The point is that dynamics will only happen, and you will only get resonance Raman intensity if the minimum of the excited state surface is displaced from the ground state surface. So there is an excited state distortion that you need to have in order to have resonance Raman intensity. That is super important. And in order to take that from obscure mathematics into more chemical origin, I've constructed a toy system for you that I hope will make things a bit more transparent. That toy system runs as follows. So here we have a totally normal organic ligand. We have a central copper and we have a chloride ion. So that is copper 2, it's a D9 system. It has a fairly simple electronic structure. So you will have one singly occupied molecular orbital. That singly occupied molecular orbital is here that in-plane sigma anti-bonding dx squared minus y squared type orbital. And then you have 4 essentially non-bonding copper-based molecular orbitals below the SOMO. That is essentially a quadratic planar complex. Then next in energy, you have the 3 chlorine p orbitals, and among them there is a nice sigma bonding orbital with respect to the copper, and even lower in energy, you have the nitrogen p orbitals that form sigma bonds with the copper. So that is a very straightforward electronic structure. Now let's look at the ground and the excited, so that is the electronic ground state. Now let's look at the excited states. Now we calculate the absorption spectrum of the toy system, and so what you will find is that you will have a few very low intensity transitions here in the absorption spectrum. So I've multiplied it here by a factor of 10. And these transitions are obviously DD transitions. So excitation of an electron from the non-bonding copper D orbitals to the SOMO. And you can look at the difference density. So that is a difference density. It's a difference in electronic density between the ground state and the excited state. That is a very nice way of obtaining insight into the nature of transition. So yellow are the regions that are depleted of electron density. Red are the ones that gain electron density in the excited state. So you see for a DD transition, there is not that much charge that is moving. That is clear because it's a transition that is basically localized on the copper ion, and that has a quadrupolar symmetry. That is also why these transitions are so weak. They're electric dipole forbidden. There would be electric quadrupole allowed, but the quadrupole intensity mechanism is much smaller than the dipole. Incidentally, I've only, for your reference, I've plotted also the circular dichroism spectrum where these DD transitions are pretty intense, and that is quite typically so, that you have DD transitions that are weak in the absorption, they are strong in the CD, and they're also strong in the MCD spectrum, but that's an aside. Now this peak here, that is a transition of pi symmetry ligand to metal charge transfer, and looking at the difference density, it comes from an out-of-play lone pair of the chlorine into the singly occupied molecular orbital. So here you lose electron density, you gain electron density. And here is the third, the most intense peak, and that is coming from the sigma bonding chlorine-copper orbital into the SOMO, which is sigma anti-bonding. So here you nicely lose electron density along the sigma bond, and you gain it in the SOMO. That is the most intense transitions, and that is generally so. The most intense transitions in an optical spectrum always arise from transitions between bonding and anti-bonding pairs of orbitals. Yeah? That gives you the largest transition dipole moment. Yeah? Now, having talked about that, I wanted to make a short digression, very briefly, and talk to you about the difference between the transition density. I've now shown you that you can nicely use the transition density in order to obtain insight into the nature of a transition. And so that difference density is basically the difference between the square of the acceptor orbital and the square of the donor orbital, yeah? Or the effective acceptor orbital and the effective donor orbital. Now, the intensity in an optical transition is coming from the transition density. And the transition density dipole moment is the dipole moment of the transition density, which is a product of the donor and acceptor orbitals. Now, and that looks different than the difference density, obviously. So you see here in the DD transition, you don't have much of a transition density. For the pi LMCT, you have that shape here that is basically located on the chlorine, and you have a very large transition density that is located along the copper-chlorine bond for that sigma LMCT transition. Yeah, and so the absorption intensity is proportional to the square of that, to the dipole moment of these densities. Yeah, it's important to keep that in mind. Yeah. Now, what does it mean for the resonance Raman spectrum? Now, let's say we tune our laser into that weak absorption band here. You don't get much of a response, some very, very weak bands. Now, you tune the laser into this absorption band or this absorption band, and you get a strong response. And it's dominated by a peak at 348 wave numbers. So, and at 348 wave numbers, now you can analyze what vibration is that, and that is the copper-chlorine stretching vibration. That makes a lot of sense, right? Now, if we look at the potential energy surface that are associated, so this is now, we look at the total energy as a function of copper-chlorine distance. Now, here is our copper-chlorine equilibrium distance, and here we have the potential energy surface of the D to D excited states, and you see there is not much of a distortion. So they have their minimum roughly at pretty much the same place as in the electronic ground state. Yeah, so that is that weak absorption here, and since it doesn't distort, it has a very weak resonance Raman response. Now, as you see here, if you excite into the LMCT states, the molecule is hugely distorted. Now, that calculation is a bit bogus because it doesn't show a minimum here on that potential energy surface. It's maybe somewhere out here. That is certainly not a good calculation. The minimum should be somewhere here. Now, let's assume it would be. Yeah? Then, then you see that you have a nice big distortion, like say from here to here, in the excited state. That does not only give you large absorption intensity, it also gives you that very strong Raman response. And why is that distortion occurring? Because you excite an electron from a bonding orbital into an anti-bonding orbital. So you make the bond a whole lot weaker in the excited states, and hence that minimum is shifting so much. And now you see how you can look at the resonance Raman spectrum and obtain a huge amount of insight into the nature of the chemical bond. Yeah, so which vibrational modes are excited gives you an enormous amount of insight into the nature of the bonding, even in the electronic ground state. That is just so beautiful, and it will require a fair bit of analysis, to really open the curtain and look behind the scenes. But once you have done it, it's a very satisfying experience, and you really can, if you combine absorption spectroscopy and resonance Raman spectroscopy, you can learn so much about your system. It is really amazing. And now here's an example from the real world, so not a toy system, and that is iron peroxo compound complex that is side-on. We will probably not have time to go into more detail. Now, that is a Sidon compound. It's a high-spin iron 3, and it has a Sidon-bound peroxide. That is the absorption spectrum, so it has a number of absorption bands here. And here you see the resonance Raman spectra that are taken at different excitation wavelengths. So here you have the resonance Raman spectrum at 676 wave numbers, so that is out here. There is not much of a response. Now you start to like zoom the laser here into this absorption band, and you will find that there is a strong vibrational band at like 800 something wave number, 816 wave numbers. Now, if you do the labeling experiment with O18, you will find that this vibrational band in the resonance Raman spectrum moves, and it moves by 5.7%, as it should be. So that is an OO stretching vibration here. And that is an OO stretching vibration that is just like the totally symmetric. It's the OO stretch that has this shape here. Yeah? And that is strongly enhanced if you excite into this band here. Now, if you tune the laser any further to 350, where you have a very big absorption band here, then you will find that there is another vibration that is hugely enhanced. Yeah? It's also oxygen isotope sensitive. And so what is happening here is that you have the FeO stretching vibration strongly enhanced. Yeah? So you have now used the isotope shifts to assign these vibrations, and now you have very different behavior by excitations into these electronically excited states with respect to that electronically excited state. And so if you analyze the electronic structure of that, and I think the slide is way further down and we won't be able to get at it, you will see that this excitation here belongs to a sigma bonding to sigma anti-bonding excitation of the FeO bond. That's why it's at FeO stretch hugely excited. Whereas these excitations belong to charge transfer excitations that come from the peroxo ligand to the iron. Actually, what's happening here is that as you transfer an electron from an O2 minus to the iron, it's that the OO bond in the excited state gets stronger, yeah, because you remove an electron from pi star anti-bonding orbital of the O2 minus in the excited state to go to a superoxo iron 2 type electronic structure, and that makes the OO bond shorter, and that is why in these excited states here you have the OO bond stretch strongly enhanced, whereas in this excited state here you have the FeO stretch strongly enhanced. So you can basically paint an experimentally derived picture of the electronic structure of your compound from the combination of absorption and resonance Raman intensity. Now, these triangles and open circles here, what they are called the so-called resonance Raman excitation profile, and that consists of measuring the resonance Raman's, the intensity of these vibrational bands as a function of excitation frequency. Yeah? So each one of these circles is like a separate experiment after you like set the laser to a given point. Yeah? And so you can nicely see how the OO stretching vibration is tracing these absorption bands here, whereas the FeO excitation is tracing that absorption here. It is actually, there are two things that are quite typical here. First of all, they are shifted relative to the absorption maxima. That is a phenomenon called pre-resonance. And the pre-resonance means that typically your resonance Raman effect sets in before you actually hit the electronically excited state. Yeah? And secondly, there is interference. Yeah? So you don't have much of an OO response under this absorption band here. And that is because there is destructive interference between the contribution from this band and this band. That's a detail we don't want to get into now, but these are things that can happen. Yeah? But again, the resonance Raman excitation profile is a different dimension in a resonance Raman experiment that you can use to your advantage. Now, I think summing that up, you will see that you can approach resonance Raman spectroscopy now from two angles. From the experimental angle, where you have the absorption spectrum, you have the resonance Raman spectrum as a function of excitation wavelength, and you can simulate these spectra using that time-dependent theory that I've mentioned in passing. The theory for that is in that paper of 2007 by Taras Petrenko and myself. And you can now use quantum chemistry to calculate all of the parameters that go into these simulations, and that is essentially the excited state distortion. Yeah, so the displacement of the minimum along a given normal coordinate. Yeah, and that is something you can calculate, and you can use ORCA to calculate it. That means using this type of methodology, you bring resonance Raman on par with EPR spectroscopy that uses an effective Hamiltonian, like spin Hamiltonian parameters, like G values and D values and hyperfine couplings and all of these things. And the equivalent of that in resonance Raman spectroscopy are these excited state distortions. It's a totally underused technology that should be used a lot more. It is available in ORCA for like many, many years. It just needs to be picked up by the experimental community more. It's a very powerful way of obtaining beautiful insight into experimental data. So, I think I have been quite a bit slower than I thought I would be this morning, and I think I just wrap up here rather than rushing you through even more information. I hope I've provided you with a bit of insight into vibrational spectroscopy. I've talked about force constants that measure the stiffness of internal molecular motion. These are stretches, bends, and torsions. The systematic way of analyzing these possible nuclear motions are normal vibrational modes and normal vibrational frequencies that describe the eigenvibrations of the molecule. Yeah? So they depend on the force constant and the masses of the atoms and geometries. Yeah? That means you can use isotope labeling to assign vibrational frequencies by changing the masses of the atoms. The systematic way of analyzing normal modes is normal coordinate analysis, and you typically will require the combination of some form of quantum chemistry with experiment in order to get to an experimentally derived force field of the molecules. Now, of the different experiment, IR spectra depend on the change of dipole moment during the normal vibrations, yeah? Whereas Raman intensities depend on the change of polarizability during the normal vibration. That will require an infinite summation over excited states if you do it theoretically, whereas resonance Raman intensities depend on the distortion of the molecule in the electronically excited state. And that is like the key feature that make resonance Raman and spectroscopy and resonance Raman intensity so powerful, is that you get local information, strongly enhanced local information. Even in a like macromolecule, you can zoom into those vibrational modes of the chromophore. If you have different chromophores, you can even study them separately. So it's a super powerful technique that is a very nice part of the toolbox of bioinorganic spectroscopy. So I think we're now 5 minutes early. You've seen I've went roughly through half of what I wanted to tell you, which means I probably have been talking much too slow. Huh? No, but if there are any other questions on the material that's in the lecture notes, please feel free to ask them. So I hope you got a little bit out of these lectures, and I will say goodbye now. I will have to leave tomorrow, but I will be around today, and I will be very happy to discuss with you. There are various group members here who will run the ORCA tutorials, so I hope that you can use that time to get your feet wet with a bit of quantum chemistry and have fun with it. And I promise it's possible. So once you start getting these calculations going, it's really a lot you can do with it, and it's also a lot of fun to do. So with that, maybe if you have a few questions, we can ask them now. And otherwise, I thank you very much for your attention. Yes.
So, in the Raman spectroscopy, where you extract the molecule from the ground electronic state to the partial state, what is
It has none. There is no significance of these virtual states. So if you look at the mathematical expression, it's an infinite summation over excited states, which is how you should think about it. That virtual state, I think, is invented by people to get a grip on the two-photon process that underlies the Raman scattering process. But there is no, it's called a virtual level because there is no reality in it. Yeah?
After certain level, it will reach the continuum, so then the molecule will dissociate.
But then you have reached an actual excited state that is just dissociative. Yeah? So quite typically, like you have an ND-YAG laser that is operating at 1,000-something nanometers because you are below the absorption threshold. Yeah, if you're above the absorption threshold, then eventually, of course, you will reach these highly excited states and you will dissociate the molecule. Actually, I think I have maybe shouldn't show you that, but there is, I had a slide where I've put in everything that can make your life miserable in resonance Raman spectroscopy. So that is my dirty laundry slide. So if you have a bad time with resonance Raman spectroscopy, it can be because you either like decompose the system, the molecule, because of overheating, or you can photodissociate once. That happens quite a bit. Yeah. So like you have your nice molecule, it's colored. You tune the laser to the right frequency. You put your sample in, and bang, it's gone. And then you say, shit. So what normally helps then is that you tune the laser just to the edge of the absorption band, yeah, to hit a pre-resonance. That will help you. So don't give up. If that happens, you can still get mileage out of resonance Raman spectroscopy by going just to the red edge of the absorption band. Then, and that is probably your biggest enemy, especially if you study organic cofactors, there can be fluorescence, obviously. Yeah? So like once you excite into the excited states and you have radiative decay, then your resonance Raman spectrum may look like this. Yeah? So that is basically a like 80-degree line. And so you can try to fish out your resonance Raman signal on this amazing fluorescence background, and that normally is not working very well. So fluorescence is your big enemy. You can help it a bit by putting like fluorescence quenchers in it, like lanthanide complexes or so. You sometimes have exceedingly weak signals, and then you have a lot of noise that happens if you excite into a DD excited state. So as a rule of thumb, like your absorption band should have an epsilon of at least 6,000-7,000 for resonance Raman experiment to make sense. If your epsilon is only a couple of hundred per molar and centimeter, you will probably not have fun doing it. Yeah. Then you have solvent, and solvent has Raman peaks, right? And if your solvent is like several tenths of molar in concentration, it may obscure your resonance Raman spectrum. So this can happen. Then you have to change solvent. And if you cannot change solvent, that's no fun. And then there are all kinds of artifacts that you will have to deal with coming from cosmic rays or other light sources, maybe like the light of your lab lamp, or like your peer opening the door at the very moment he shouldn't have. And so that leads to resonance Raman spectra that look like this. They have these spikes. And you can also have plasma lines from the laser that look a bit miserable. There are ways to deal with all of this, but it's not the easiest technique in the world. Yeah, so it is quite a bit more involved than absorption spectroscopy. Okay, that was a very long answer to a short question. Then is there another one? Then? Yes. Sorry. Sorry. Two-photon absorption, yeah, there is like hyper-Raman scattering that is that kind of experiment. That is like deep into the field of specialty of like nonlinear laser spectroscopists. I'm not aware that much of that has been used in bioinorganic chemistry. You see, this already complicated enough.
Here.